Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Meredith MacGregor with us today. Hello, Meredith.
Hi.
And Meredith, on this 23rd of April, 2025, as we record this, what is your geolocation? Where are you at?
I am in my office at Johns Hopkins University.
Aha. I think the editor-in-chief is somewhere around
He's
there.
right down the hall.
Hi, Ethan. Okay, well, we have lots of action going on at my house, so we'll just try and ignore all that. Let's see. In the spring in the air in Baltimore, do we have flowers
It
out,
is.
trees yet?
Yeah, it was like super cold last week and then it suddenly got hot. So it almost feels like summer. It's like 80 degrees here.
Nice, nice. 80, that would be cool for where I'm at. So I'm in Phoenix, and we hit our first triple digit F about a week ago. And so we're sort of still oscillating, but yeah, we are definitely into the upper 80s and 90s at this point. So very cool. And you got some pretty awesome little toys over your shoulder there. You got some
Yeah,
little spaceman. That is so awesome. Very
I
cool.
got lots of stuff.
You got lots of stuff.
I spent a lot of time decorating my office. So I have like a model of the Sophia
Yeah, yeah.
plane in the background, and I got the like women in like NASA like Lego stuff.
Yeah.
And Anna's favorite thing, which I don't know if you can totally see, is like the very top shelves. I have these like pictures up here.
Yes.
Uh, I taught a class on life in the universe that was like a gen ed class, and
Yeah.
I gave students like a final project where they could do a creative expression of a research project. And so
Perfect.
my student did the Drake equation, but like
Perfect.
illustrated on canvases.
Perfect. 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 Yeah, I use that same technique in my teaching as
Yeah.
well. Have them do something creative at the end. It's very good. Very good. Cool. And Meredith, what do you like to do for research?
So I do mostly observational work, and I always say I broadly focus on trying to understand how planetary systems form and evolve over time, and I'm especially interested in how they might become habitable.
Very cool. Awesome. And that is going to bring us to this very awesome. Make sure I hit the right button here. I don't end this one. Sure. This very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Proxima Centauri campaign. First constraints on millimeter flare rates from ALMA. And Meredith, take us away.
Yeah, great. So I'm super excited to get to share this with everybody. I'll start by kind of highlighting that I get to be here and talk about this, but this work was really a big collaboration. So the first author is actually Kiana Burton, who was my PhD student. She graduated last summer from CU Boulder. And so she really did the bulk of the work on this.
Mm-hmm.
Uh, but then, this was a pretty large observational project.
Yeah.
And so there's a large team of people. So Rachel Austin is here at Space Telescope. Ward Howard was a postdoc working with me at CU Boulder. And then Alicia Weinberger, Evgenia Shkolnik, David Wilner, Jan Forbrick, and Thomas Barkley, sort of all over the place, all experts in millimeter data analysis, stellar flares, and all were big parts of this campaign.
Very cool. Nice, nice collaboration. Good shout
Yeah.
out. Okay.
Yeah, so let's just jump in.
Yep.
So what really motivated doing this research is this kind of question I have about, how do we form habitable planets? What makes them habitable? And so, it turns out that a lot of the exoplanets that we've discovered and are now looking at with JWST and trying to think whether they're habitable or not and look at their atmospheres orbit M dwarfs. Um, Many reasons for that, right? M dwarfs are the majority of stars in the galaxy. They're like more than 70% of the stars. And they're also nice and faint, which means that the planet makes a larger dip when it transits in front of the star. And so we have tons and tons of potentially habitable planets that orbit M dwarfs. But M dwarfs are tricky little stars, right? They are super active. And
Yes.
so they routinely send out these bursts of, high energy emission that we call flares, and then also bursts of high energy particles called coronal mass ejections. And the thought is that these will impact the atmospheres of any planets that are orbiting these stars. And the
Absolutely.
question is, what is that going to do, right? We don't fully understand M-dwarf activity levels across the whole electromagnetic spectrum.
Yes.
So we actually don't have the best constraints on what like the flare spectrum is to even put into atmospheric models.
Fair.
And then, if we knew that, we still need to think about their photochemistry and how these flares and coronal mass ejections might actually shape the chemistry of the exoplanets itself. And that can look like just dissociating molecules. It could even, in extreme cases, drive atmospheric escape and remove atmospheres entirely.
Yep. Very
Um,
cool.
so, in my mind, if we're in the era of trying to look at atmospheres with JWST, then we need to actually know what the heck the stars are doing in order to
Mm.
inform those observations that we're getting. So I, do a lot of work with ALMA, imaging disks and planet forming environments.
Yeah.
And it turns out in the center of these disks are stars, and the stars do lots of interesting and exciting things.
Yes.
And I got interested in Proxima Centauri, a number of years ago because there was some ALMA data taken that showed kind of an excess of emission from the star at millimeter wavelengths.
Okay.
Initially, that was interpreted as due to a disk, right, where the
Okay.
stellar radiation is heating dust particles around the star, and those are then glowing brightly at these longer wavelengths. And so when you see an excess of emission above what you'd expect from the photosphere, you're actually seeing this kind of disk.
Yeah.
So I had been curious about that because, there was no resolved imaging of this disk. And so I grabbed that old data set and I reanalyzed it in a time-dependent fashion. I
Okay.
basically, that data set had been roughly like 13 hours long. And so I started by just imaging each of the hours separately. And
Cool.
it was extremely dramatic. If you looked at like the first 12 hours together, you could see nothing at all.
Okay.
The star was not even detected. And
Ooh,
in the last hour of observations, it was like super bright.
bang. Okay.
And then if you went and narrowed it in even further, what we showed in that 2018 paper was actually there was only emission from the star in like 2 minutes where the star underwent this like huge burst. And actually that light curve is shown in this paper as like the second figure. So if you scroll down to figure 2, you
Yep.
can
Take a
actually
look.
see that light curve.
Light curve. Ooh, nice.
Yeah. So this data was taken in 2017, and we published the original study on this in 2018. And this was the entire like excess of emission that was detected when you took all 13 hours and averaged them together was actually because the star had brightened from being like undetectable to 120 millijanskis in
Yikes.
like a few seconds and then
Yikes.
faded back down.
Okay.
And so if you took, a couple minutes of 120 millijanskis and averaged it with 13 hours of non-detection, you ended up with a point source that was like slightly above the photosphere.
Yes.
So,
Very.
bad news for dust in the system, right? Like
Yeah.
that gates needing a disk to explain the brightening. But it opened this kind of entirely new window on stellar flaring because before that, we had not really studied flares with ALMA in the millimeter wavelengths. There was lots of work being done on stellar flares in like the optical and the UV and the X-ray. And then
Yes.
there was lots of work being done in the long radio wavelengths. And we
Yes.
kind of like ignored the middle. Um,
It's kind of
Turns out, right,
yeah.
stars do flare across the entire electromagnetic spectrum.
Yeah.
But we knew almost nothing about their millimeter properties. And so I set out to try and like take that result and grow it into a much bigger understanding of like what the heck is happening at millimeter wavelengths, how frequently do they flare, what are their properties, how does it fit into kind of the larger multi-wavelength picture.
Cool.
And so that's where this project came from. I'm calling the Proxima Cen campaign, which is that I set out to convince a whole ton of telescopes to let us stare at Proxima Centauri for roughly 40 hours
Mm-hmm.
straight.
Mm.
Uh, so we had ALMA on the ground, and then this huge suite of observatories that are listed here. So we had Chandra and Swift, and it's in that paragraph that you highlighted, like just
Yep.
above there. Yeah, the whole
Okay.
list of telescopes. And that Hubble and TESS, and then we used
Okay.
the DuPont telescope to do spectroscopy from the ground. It was this whole big campaign. We had,
Very nice.
9 different facilities
Yeah.
that we coordinated the observations, and we spent roughly 11 nights,
Oh,
which are what are listed in table 1,
very cool. Very
which is, I think, right on the next page.
Yeah.
So
Okay.
these are the nights that we actually observed. So we did this because we had these ground-based optical telescopes, so we coordinated to be nighttime in Chile. And so
Nice.
we like pinned these observations to happen kind of overnight in these like 6 to 8 hour chunks on 11 nights, starting from April going into July, where we just, got all the telescopes to look at Proxima Centauri for 10,
Oh, that's great coordination.
50
Very
hours.
nice. Very nice.
Yeah, it turns out it's really hard to do this, and you don't appreciate how many problems happen in telescopes until you like try to get 8 of them to all look at the same thing at the same time. Um,
It
I
worse than herding cats, I hear.
it absolutely is. I have this like Excel spreadsheet that sometimes I show in talks, which just has like night of scheduled observations and then telescope, and then I colored all the boxes based upon like red, no data, like
Good, yeah.
yellow, some data, green. We actually got everything to work. And there was just so much shenanigans that happened. Like one night we were supposed to observe with Alma, and we didn't because it snowed and they lost power and it shut
Oh
down the
no.
observatory. And there were multiple nights that we lost, like Hubble observations, because this was a period that Hubble was having problems with its gyro wheels.
Yes,
And
yes.
so it was basically like going, trying to point at the initial guide star, failing, and then like doing no observing. And you didn't know that until the next day, right? You would get this thing that was like,
Ouch.
just kidding, we didn't actually observe your target.
Ouch.
Um,
Okay.
so
Well,
it was a whole mess.
I applaud the attempt at the symphony, right? You're trying to do a symphony, and not everybody was warmed up yet or ready. So very good.
Right. So we did actually get a huge amount of data and much more multi-wavelength coordination than I thought was possible. And it turns out you get some really cool science when you actually are able to like stare at one source for that long with that large a wavelength range. So
Mm,
we published one paper from this campaign in 2021,
mm,
which was this extremely dramatic flare that we saw. It was like the largest flare that we'd ever seen from Proxima Centauri with Hubble and ALMA simultaneously. And in the Hubble data, it brightens by like 15,000 times from the quiescent to the peak of the flux.
okay.
Um,
Okay.
and with this data, we have really exquisite time resolution, so we can look in like 1 second bins. And it turns out that, the whole flare where it brightens by that amount was like 8 seconds.
Okay. Okay.
So there's some crazy things happening here, right?
Wow.
And what this paper then is digging into just the ALMA data from that.
Okay.
So there's a bunch of multi-wavelength data that we've published in several papers so far. There's that paper from 2021. Ward Howard led a paper in 2022 that was looking at some of the Chandra data and
Yeah.
how it correlates with the ALMA data. But Kiana basically took the entire chunk of ALMA data and just did like the definitive analysis of all the millimeter flares.
I like definitive analyses.
Yeah. So, we're going to do more. There's still more work to be done, honestly, with this data set to actually look at the flares across all wavelengths.
Yes.
Because as it turns out, we see these time delays sometimes between different observatories. And so there's this trick of like, how do you line up different
Yeah.
flares
Yeah.
and know that it's the same flare, even if there's a time delay between, say, the optical and the millimeter.
Okay.
But this is all of the millimeter data analyzed in one fell swoop. And so she took that 2019 data that we did as part of that campaign, and then she also grabbed the data that had been taken in 2017 and
Yes.
reanalyzed it. And
Okay.
then there was some further observations of Proxima that got done in 2021. And so she grabbed that data as well. So we basically like took our data set and then went into the ALMA archive and grabbed every other time that ALMA had ever looked at Proxima Centauri and
Okay.
just took them all together.
Nice. Very.
Um, yeah. So big data analysis task. And then what I think was a huge piece of analysis was this part here, which is just like trying to identify flares. Because with ALMA, it's an interferometer, right? And so what you actually are sampling with the telescopes is the Fourier transform of the sky plane,
Correct. Yes.
right? So it's not
Yes.
as easy as an optical telescope where you just straight up get your light curve out. So what Kiana did was write this huge pipeline where actually she fits point source models to the UV, the millimeter visibilities
Okay.
in each integration time. So the integration time with ALMA for these data sets was about a second.
Right.
So what she does is we take like 1 second of data and we fit a point source model to the visibilities, the native Fourier transform plane,
Yes.
and get an flux out of that, and then record the timestamp and that flux. And then step through the entire data set, basically fitting a point source model to every single integration, and then constructing a light curve from that.
Very cool.
We do it that way because once you create an image, you have to go through this inverse Fourier transform, and you use this algorithm called clean. And clean is non-linear, which means that you lose the true uncertainties on the data. So if you want to really get a model with a real uncertainty on it, you have to do it in the visibility plane. And so by fitting the point source models in the visibility plane, we get the fluxes and their true uncertainties.
Yes.
So that was like step one in Kiana's pipeline, was to do this. But then, we have this light curve that is over 50 plus hours of data, and that's huge. And it's all in 1 second integration times.
Correct.
So it's impossible to go through that by eye. There's no way anybody's going to sit there and like comb through that data set looking for flares. So then she added to this pipeline a bunch of steps that try and automatically detect times when there are candidate flaring events.
Okay.
And so we do that by essentially computing the flux in the lower and the upper sideband with ALMA. So ALMA doesn't observe at a single frequency, it observes at what we call a bandwidth. And that's split into two pieces. There's a lower frequency sideband and an upper frequency sideband, and they're each like 4 gigahertz wide.
Oh, okay.
So she actually fits a flux to the whole data set and then to each of those sidebands.
Okay.
And then we identify things where there is a change in the flux of more than 3 sigma. And then we use a comparison between the lower and upper sidebands to kind of vet whether we think it's real or not. Like if you see a flux change in only one of the sidebands and not in the other one, then that's not a great indication that that's real flare. Whereas if they both kind of go up at the same time, then that indicates that, you didn't have like a fluke in your data set. So we, make this list of candidate flares and then go through this vetting process. And then ultimately, there's parts of this where we actually create images of each of those, and you can look at those by eye. And in the end, we come up with like a total list of flares. Like these are the things that are above the noise level that we feel pretty confident are like real things. And that is, for the total data set, we detected 463 flaring events.
Right.
Which is like a lot.
Considerable. Yes.
So
absolutely.
Big sample of flares. So some of these are really bright. And so some of those example light curves are what's in this figure here, just to kind of show what those light curves look like. The biggest one was the one we already looked at in figure 2, which is like this 120 millijansky flare. These 4 are other like decently large ones. And so this is just showing, flux density as a function of time. Time is relative to the peak of the flare. So on each of these axes, 0 is the peak. And then what's overplotted in red is actually a best fit flare model. And so that is using Guadalupe Tovar Mendoza's flare template. And so you can see that each of these flares is described pretty well by having like a really bright phase where they kind of follow this kind of sharp rise, and then this sort of slower exponential tail.
Yeah, yeah, it's a little asymmetrical on the downside.
A little bit, yeah. The interesting thing with these millimeter events is that, in the optical, you'll often see these flares that last for like maybe an hour and have these really nice long decay times.
Right.
These data points are like a second. So these flares are really short, right? I mean, these flares are all on the orders of seconds in length. So that is kind of a notable thing, I'd say, about the millimeter flares, is that they all appear to be quite short. We have not observed a flare in the millimeter that's more than maybe like a couple of minutes long.
Yeah, we don't get hours here. We're talking minutes at best.
Yeah. So that's different than flares at other wavelengths. And that's kind of an interesting thing to dig into, trying to understand like the physics of why these millimeter flares look different than they do at other wavelengths.
Yes.
So this shows you, that these really do look like flares, right? They brighten significantly. These things are on the orders of like 40 to 100 millijanskis. Like we didn't do something really sketchy digging around in the middle of your visibilities. And then for these really bright flares, the table that comes after this, we're able to actually do some more analysis. So, if it's not that bright, we just get a total flux out. If it is above a certain significance level, then we can actually look at things like the spectral index, which is that alpha spectral there, and we can actually place a lower limit on the linear polarization.
Nice.
And that's because ALMA observes in this, band, two different bandwidths that are separated in frequency. And so we can actually fit the flux in each of those band passes and then fit for the spectral index across.
I'm with you. What is the half-life of what here?
So that's the half-life of the flare. So that comes from those red models in that figure. And that basically fit a full width half max, like T1/2 value for the width of that model flare.
Thank you.
Yeah. So the spectral index is the spectral change with frequency. And so if you were, say, a totally Rayleigh Jean's tail, like you would expect with just a photosphere, right? You would expect that this has a value of 2.
Okay.
But what's interesting about the millimeter flares as a kind of population is that we have gotten this like really interesting range of values.
Positive and negative, and sometimes rather large.
Right. And so what I think is most fascinating is actually, some of the ones that are the negative ones are like really interesting.
Yeah.
Because these show that there's like a how am I trying to say this? The spectrum is diverting from being like a Rayleigh Jean's like black body tail, right?
Yeah.
And so that gives us some clues as to kind of these like negative spectral indices, give us some clues as to like potentially what the emission mechanism might be.
What the driving physics might be.
Yeah.
You would get such variability between pluses and minuses.
Yeah, I mean, it's interesting. The one thing that I took away from this, right, is that the ones that are all positive have actually huge error bars on them. And so they're all like overlapping.
Yeah.
Right? So it's like, 2.3 plus or minus 3.1, 2.2 plus or minus 3.5. And that's honestly because a lot of those ones are the fainter flares. And so in order to do this, basically, we're dividing the signal into 2. So this is why we can't do it on every flare. Like if you're only 4 sigma and then we split it into 2, you're only 2 sigma and we can no longer actually constrain the spectral index.
Yeah.
So like something that's at this 50 millijansky level is kind of sitting right on the boundary of where we can reasonably do this analysis, unfortunately.
Okay.
So the other, clue to the emission mechanism then comes from this linear polarization fraction. So ALMA, to do full polarization and get the cross products, is a special mode but you can always get the XX and YY polarizations. And so
Yeah.
you can use that to kind of place a lower limit on the linear polarization fraction, which is this Q over I.
Oh, mhm.
And normally we would expect a stellar photosphere to be unpolarized, so there shouldn't be anything here. But for some of these, we have quite significant like lower limits on the fractional linear polarization, right? Like
That's
this shows that during the flare peaks,
what.
we are actually seeing some evidence for polarization. Now we can't tell if that's just linear polarization or it's circular polarization because we don't have the cross products.
Right.
But you know, putting those things together tells us that at the peak of these flares, we have emission that is not described by like a black body spectral index and has some polarization to it.
Indeed. Sometimes
And
rather large, right? 0.83 is pretty good.
yeah. And so we interpret this as being that what we think we're seeing at the millimeter is actually either optically thin synchrotron or gyrosynchrotron emission.
Okay.
So at the long radio, we know we're seeing those kind of synchrotron and gyrosynchrotron emission, but usually we assume it's optically thick. And so the fact that we have this like different spectral index
Mhm.
paired with this indication of polarization suggests that actually we're picking up the optically thin side of that gyrosynchrotron or synchrotron spectrum.
Because it doesn't have time to come back. Right.
Yeah.
Okay. Mhm.
So
Uh,
this is kind of the first like really big sample of these millimeter flares, and they're consistent with what we've seen kind of from the handful we published before, right? So we have, the previous one from Proxima. There was one detected from AUMIC. This is now a big sample, so it's the first time that we can look at this like statistically. Still small number statistics, of course, because it's a pretty small table, but we are like building up a population of these large millimeter flares, and it's starting to kind of give us some clues as to what the emission mechanism is.
Very cool. Okay.
Um,
I'm
the
with
real kind of like take home from all of this is then what's shown in the last figure of the paper, which is, we detected 463 total flares. And so that's enough of a sample that we can make what's called
you.
a flare frequency distribution.
Yep.
So this plots like cumulative flare rate per day as a function of flare energy.
It's very
Um,
cool. Okay.
and so this is something that's done, commonly in stellar flare research. You see
Yeah.
flare frequency distributions all the time from like test optical data. Um, and so the blue points are all of our flares plotted. And, the one that's on the far right there,
Yeah, this
that's
outlier out here.
solid point, we exclude from our best fit.
Okay.
That's that extremely large flare.
Um,
Uh, and, to get to this plot, you have to basically determine a cumulative flare rate. But
yes.
the rate of really large flares like that is low. So the uncertainty on it is very high because, we observed for a certain amount of
Um,
time and we saw this really big flare. Maybe that means that it has a really high flare rate, or we just got lucky. And so we're biased up. So, I've had lots of people look at this plot and be like, oh, it looks like there's a break in the power law distribution, that there's one power law that describes the smaller flares, and then it looks like there's actually more flares occurring at these, higher energies, and that maybe you should fit a
maybe.
second power law. We don't do that because I don't think we have the data yet to support that, right?
Yeah, right. Right.
But
Maybe.
the rates, right? And so you need to observe for a lot longer or many more sources to get enough flares at those higher energies to really like pin down their rates of occurrence and see whether that's real or not.
This is really cool. This is the first time I think I've ever seen a cumulative on M-dwarf flare for Proxima.
Yeah, and we have certainly never ever done this in the millimeter before. So this
Yeah,
was
very
like
cool.
first time.
Very
Uh,
cool.
So the like red line with the gray error bar is the actual fit that we do to the flare frequency distribution. I believe we have the equation someplace in here for how we describe the flare frequency distribution. Equations aren't actually numbered, but it's the one on like page, yeah, it was right there, page 5. So the energy is described in the equation above, so we can calculate the energies from the flares,
Yep.
integrating over the total time and the
Yeah,
total bandpass, and
great.
then that turns into the flare frequency distribution.
And then that gives you the flare. I'm with you on that one. Okay.
Yep. And so we fit then for that alpha distribution, which gives us like the power law index of this power law, right? So we're basically just saying the rate of flares as a function of energy is a power law. And that's not new, right? I mean, every time we've made a flare frequency distribution at any wavelength, it's always a power law.
Always.
The power law in astrophysics, apparently. But we can fit for the index. And what's interesting about this result is then we can compare that to what we get as the index at other wavelengths.
Cool. Yes.
And that's where things are kind of unique. If you compare that power law index that we get, which, you know, the cumulative index is like 2.92 plus or minus 0.02, it's much steeper than what's measured at other wavelengths for Proxima, like the optical and the X-ray, where the power law index is something more like 2.
Okay. Wow.
It means that there's a lot more small flares happening in the millimeter than we see at other wavelengths.
Why is that?
And that's interesting. It suggests that, you know, there might actually be a pretty high rate of these little flares. And even if they're little, there's enough of them happening that they might actually be quite important in terms of like the actual radiative output from the star.
Oh, yeah.
And it's especially intriguing that this is different at the millimeter versus, like, say, the optical.
That is so curious.
Because, you know, I think what we're really getting at with data sets like this is now we're getting enough flare data to be able to look at how the flares behave in different wavelength regimes and try and understand kind of a multi-wavelength picture of the underlying flare physics, and then which of these wavelengths are really reliably tracing, you know, the energetics and which ones maybe are not.
Secondary, for example, yes.
Right. So, you know, I find this really intriguing because the millimeter and the UV in some of the work we published earlier really trace each other very closely.
Okay.
And it's this high energy UV radiation, right, that's most damaging to atmospheres.
Yes.
And the optical has not traced these two quite as well. And, you know, not totally ready to commit to anything yet, but that's suggestive that maybe the optical isn't tracing the energetics of these flares as well as, say, maybe the millimeter and the UV are.
I won't hold you to that, but okay.
Yeah, don't.
We'll come back to that point, though. I'm going to come back.
More work needs to be done.
Yeah, I'm going to come back to that.
Yeah, but, you know, I think there's a lot more to be done here. And this is the first time we've ever been able to do this with ALMA. And it's so cool. It's pretty exciting to be able to like be doing millimeter flare work for the first time.
Very, very cool. Very cool. And I'll just walk through the rest here. We have the discussion. We have talked about the polarization, the temporals.
Well, I think most everything that I talked about with the figures, but, you know, written out in text.
Yep, 8 sigma. So, you know, it's real.
Yeah, so that's the level at which we're able to then split it and do that analysis, because, you know, if it's an 8 sigma event, then in each sideband we're still getting like a 4 sigma detection.
Very cool. Very nice. All right. Awesome. Meredith.
And I guess the other thing worth pointing out here, right, is that we have had on that last page, there's a reference to this Kirker et al. Paper from it's a review paper of solar flares, because there is some limited sample of like solar flares that we've measured in millimeter wavelengths. What's especially perplexing is that they show the exact opposite in the spectral indices. So you would think that like this would be a, you know, there's a good analogy to be drawn between like solar flares and M-Dwarf flares, but they show very different behavior in the millimeter. And it is not immediately clear like why that is yet.
Yes, well, I guess the one thing I would say is half a solar mass is not one solar mass.
Yes, and it's possible that like we're just seeing different parts of the spectrum as well. the spectral index results like imply that the millimeter synchrotron spectrum is like rising out towards the radio, and then there's some turnover point, and then it starts heading down again. But since like we're only seeing this side of it, and then we've only really seen that side of it, we
Yeah.
don't actually know where that peak is.
Yep. Got
Yeah.
the ones, big ones. Very cool. All right. Very nice. Meredith, I want to thank you so much for walking us through your very awesome article. Thank you.
Yeah.
And you kind of mentioned it a little bit at a couple points. So let me go ahead and push on that part a little bit. And where do you think we go from here, given the published article? Will there be a forthcoming article that will go through all of the wavelengths? Here we just did the millimeter. There's always more observations to take. What does it take to get 4,000 of these flares, right? Order of magnitude more rather than 460.
Yep.
Tell me what it takes to get 4,000.
Good question. Yep.
And of course, is there some theoretical modeling that needs to be done to explain A, the emission itself, or B, why it's so different than, let's say, the sun or something? So next steps, where do you think we go?
Yeah, so totally lots of different directions, right? So we're still working on the data from this campaign. So yes, there will be, forthcoming articles when I manage to finish things in the, infinite time that I have of actually like looking at the full correlation between the millimeter and these other wavelengths of emission, right? Because there's a bunch of questions in my mind that come out of this. Like one is, how does the millimeter tie in fully to all these other wavelengths? And so we need to look at that. Then there's just kind of like, we want to get more millimeter flares to really understand the millimeter flares as a population. So Kiana, for her thesis, had looked at like 5 more M dwarfs with ALMA, where we got like 10 hours on each one. And so, paper that will be coming out sooner is the analysis of then the flare frequency distribution for all 6 of those M dwarfs with ALMA. And so we can actually start to look at, is this steep power law index the same across other M dwarfs? Is Proxima just like a really weird star?
Yes.
It's definitely a weird star, but is this common amongst M dwarfs? And does it change with age and like subspectral type?
Oh, that's an interesting question. Yeah, sure.
Yeah. So that gets us a little bit there. And then, that doesn't get us to 4,000 flares, right? Like you asked, we really need to build up the statistics. And so ALMA proposals are due tomorrow morning. And I have been spending my last week busily writing
Not at all.
large program to try and do this for a big sample of stars.
Well, I wish you the best of luck on that proposal, right? And I hope, hey, TAC, if you're listening, thumbs up. TAC, thumbs up. There we go. Very cool.
Yeah. So I think there's a lot to be done.
Yeah, and it'll be really exciting to see this develop over the next couple of years, both across different M dwarfs, piecing together the whole, SED across all the wavelengths. It'll be really cool to see. So
yeah, there's a lot of, interesting results now coming out of JWST too, because we also haven't really studied flares in the near IR, and it turns out stars are very active in the near IR.
Yeah, very exciting. It'd be really cool to see this. Very nice.
Yeah.
Meredith, I want to thank you once again for walking us through your very lovely article and sort of the short-term-ish future of M dwarf flaring. So very cool.
Yeah, thanks for having me.
Sure. And that will do, everyone. And I hope this made your flaring astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.